This is going to be a lesson on the area of a parallelogram and a triangle. Now, to begin this discussion, we're going to see how we can actually construct a parallelogram from a rectangle. So let me start by drawing on a rectangle. Now the first thing that I want you to imagine is that there are hinges on the corners of this rectangle. Then imagine that all 4 of these hinges are connected by solid pieces of wood, so they can't really change length. Now we'd like to figure out what would happen to the area of this structure if we were to secure the bottom and push the structure to its side by a little bit. Now the real question is, do you think the area of this rectangle has changed once we've performed this deformation to it? Now, most people I asked this question to the first time would say, no, the area has stayed the same. But I think I can really easily convince you that the area has in fact actually gotten a little bit smaller. If you look really carefully, there's this tiny little piece of missing area at the top, which means that the height of the rectangle has shrunk, and that means that the area has also shrunk as well. Now if we go ahead and actually restore the original rectangle, we can use this to find a general formula for the area of a parallelogram that's been distorted like this. Now given any parallelogram, we can always cut this piece over here and move it over here as we did before. Now as you can see, the area of this blue parallelogram over here is actually identical to the area of this rectangle over here. And this actually gives us a really good way to find the area of this parallelogram. There are many cases where you won't actually have direct access to this height h, but you will actually have access to this side over here that I'm going to call a. When you actually want to measure this length a, you're also going to need access to this angle over here, which I can call theta. You also have to realize that this angle over here is a right angled triangle, since h is perpendicular to b. Now if we go ahead and use the sine of theta, we know that it's the opposite side divided by the hypotenuse, so the sine of theta is just h over a. Now we can just go ahead and multiply both sides by a to get the fact that h equals a sine theta. Just be careful here, we're saying that h is a times the sine of theta, not the arcsine of theta. And now, given this information, we can rewrite the area of the parallelogram using this information. And now, given this information, we can actually find the area of any parallelogram we want. And now we turn our attention to finding the area of a triangle. It turns out that if you cut a parallelogram in half, you actually always end up with a triangle. Now since a triangle is just half of a parallelogram, we can say that the area of a triangle must just be half of the area of a parallelogram. Now this means that we can write the area of the triangle in terms of this form of the area of the parallelogram, or this form of the area of the parallelogram. Now these formulas are really useful to find the area of any triangle or parallelogram. So to show you this, let me bring out a page and give you an example. Now if we wanted to find the area of this triangle over here, we could just see that this side is a, this side is b, and this angle could be used as theta. If we just go ahead and slap this into our calculator, we can go ahead and find its value. Alternatively, we can remember that sine 60 has an exact value, so we can go ahead and draw on our special triangle to remember that sine is just root 3 on 2 divided by 1, so the sine of 60 is just root 3 on 2, which we can write down 2. We notice that these 2's cross out to just give us our final value of 3 root 3 on 2. If we put this into our calculator, we notice that it's also equal to this 2.598. Now if you look at the picture of the triangle, it looks like we are roughly covering 2.5 squares. Notice this is 1, this is 2, and this is another half. And with this we've actually completed our example. And now we've actually completed our discussion on the area of a parallelogram and a triangle. We notice that a parallelogram's area can be given times the base times its height, or as AB sine theta, and we can half both of these values to get areas of corresponding triangles.